Hi, welcome to updated 2.8.
Part B.
Yeah,
Sorry, we had some technical glitches with it, and we had to split it in two. So,
yeah. I'm not actually sure what happened. I think it just corrupted when in the middle of it when it was processing it. I'm not sure, but it sure enough, every copy I had of it died
yeah.
after the last slide.
Okay.
So,
Well, we'll pick up here. So we had finished the last slide. So let's talk about R squared.
so when you're looking at your linear regression, when you take, and we talked about the R value, if you square the R value, you get what's called the coefficient of determination. If you square root the coefficient of determination, then you get your R value that we've been talking so much about, okay? R squared is the proportion of variation in the response variable that is
The Y.
explained by the explanatory variable in the model.
That's right. Okay. So you're going to want to learn this sentence, the blank percentage, and that's going to be whatever you get from your data or from your experiment. And you'll have to say the Y value, whatever the context is, whatever it means, is accounted for the least squared regression with the whatever the X value is, and the remaining percentage. You have to actually do a little math here, subtract from 100, and for what other potential factors. Now you actually have to come up with something. Okay.
Right.
Okay. So let's try one.
So write this down on a piece of paper, because if at any point, like maybe on a quiz that's coming up, I ask you to explain R squared in context, this is the sentence I'll be looking for, okay? This exact sentence, word for word, with just the problem information put in, okay?
Really not too bad. You just have to insert. So let's, you'll see it in context here.
Okay, so.
Trucks. Yay, our trucks again.
Trucks. Suppose we wanted to predict the price of a particular used Ford F-150, but we didn't know how many miles it had been driven. So we don't know how many miles are on it. Our best guess would be to use the average cost of a used Ford F-150, which is $27,834. That's your mean Ford 150 used truck cost.
Right, that was the, yep.
Of course, this prediction is unlikely to be very good, as the prices vary quite a bit. In fact, the standard deviation from that $27,800 price is actually almost $10,000.
Yep, so they're all over the place.
Yeah, I mean, there's just a lot of variation in truck prices. If we knew how many miles the truck had been driven, we could use the least squares regression line to make a better prediction. How much better are predictions that use the least squares regression line when we know miles driven rather than just the average price?
Right. Okay.
That's R squared.
That's R squared.
Okay.
Now that's a lot of verbiage there, but
yeah,
the line is that percentage, that R squared percentage, better than just than using a guess.
Just the mean, right?
The mean guess. Okay. Now so that hopefully makes a little more sense, but we'll go back to the trucks. We found the R squared value to be 0.66, and we say 66%. So putting that trucks into that template sentence that Miss Young had a minute ago, you want me to read it, or you just keep going, or you want to try to explain it as you go? I mean, I'm just going to do what she said. She had the template, so I'm going to put 66%. You see it right. You see the 66% right here. And I guess I could actually annotate that. Let me do that. So I'm going to just straight up insert that 66% there. And that came from the R squared value. So I'd say 66% of the variability of, and I have to talk about the context. So we're talking about the Y value, the price of the Ford F-150. You don't say the Y value. You have to tell me the context. Is accounted for by the least squares regression of the X value of miles driven. And I inserted that. And then where did the 34% come from? If you really are struggling, you have to do 100 minus 64 or 66. And if you need a calculator, you're welcome to use it, okay? But that's where the 34 came from. Now, this stuff here, they don't care. You don't want to say it's due to unicorns. Okay, something related to truck. It could be, you know, the condition of the truck, age, color, that features. There's a plethora. Anything that has to do with the context is acceptable as an alternative. Okay, or as an explanation for the other percentage.
And we don't ever expect you to do this by hand, but here's a visualization of kind of what this problem is saying. On the left-hand side, you've got just the graph of the mean truck price, which was that $27,000 truck price, right? That's your first graph. And then your second graph, you've got miles driven and the least squares regression line calculated with miles driven. So first one, not considering miles, second one considering miles, okay? And then you look at the difference and you end up with that 0.66. So that's kind of where that's coming from, is what happens when the line now takes into consideration that second variable, which is miles driven, okay? And that's why it says accounted for by the least squares regression line with x equals miles driven. That's why that part's in there, okay? So both standard deviation of residuals and the coefficient of determination are calculated from the sum of sum of squared residuals, which you saw in the previous slide. They also both measure how well the line fits the data. The standard deviation of the residuals reports the size of the typical prediction error in the same units as the response variable. So we saw you've got S is $5,740, but the value of R squared doesn't take into consideration units at all. And it's usually expressed as a percentage. Like you would see R squared as 0.66, but generally we would say 66%, yeah. Right? Because these values assess how well the line fits the data in different ways, we recommend you follow the example of most statistical software, which is you're just going to go ahead and report both.
Okay. And you're not going to generate it generally on the AP exam. They'll provide it just like it is here. They'll give you the values and you have to interpret. Right. So I would be looking for this case, and since she did the spleen and I'm going to do the writing, so I would look at this and I would be looking at the R squared value of 0.717. So I would go in here and say about 72. I could make that 72% if I wanted. Okay, I could say 71.7% either way of the variability in the, what is the Y value? The Y value is male earnings. So I need to put male earnings in here. Okay, is explained by the least squares regression with X. So I look at the X values are female earnings. And honestly, I'm just robotically putting those in to that template. You need to know that template is, you may be able to use it on a quiz, but on the AP exam, you have to have it memorized. The remaining, now I need to do the remaining 72 away from 100 leaves me 28. And I could, I mean, if I needed to, I could confirm that. Now it could be due to other factors. Another factor that might affect the relationship between male earning might be experience.
Could be location of job. You know, a lot of, like if we were comparing a teacher in Arkansas, a teacher in Central Arkansas versus a teacher in Northwest Arkansas, there's quite a big difference in earnings. So you could also, like if you were trying to compare female teacher in Little Rock to, or Hot Springs to male teacher in Bentonville, it wouldn't be gender, it would just be location.
No, it would be geography, yeah.
Right.
So, and you don't have, I mean, I don't know if there's a fixed number of them. I mean, you could have come up with other things, you know, it could have been 3 factors. But again, don't put unicorns down there. Put something that's plausible. Okay?
Yeah.
All right. Did I do good, Ms. Young? Did I pass?
I think it's so good.
Oh, good. Thank you.
Okay. All right, so let's look at let's look at this graph. The X variable is mental health disorders, and the Y variable is revenue in video games. Revenue in video games. And I think we've actually looked at this graph before. So we just want to make sure that we can interpret slope, y-intercept, correlation coefficient R, and coefficient of determination R squared. Bless you, Mr. Bobby.
Thank you.
So if we want to explain slope in context, the first thing we might want to do is look at slope. So which one is slope?
Well, we have the equation y hat is equal to negative 38 or 39.13776 plus 0.000, a bunch of ones and the zeros and one and an x. So I want the one in front of the x. Remember, statisticians do y hat equals a plus bx. So I want that 0.00, how many 5 zeros? Okay. And we were talking about this in,
well, it's just
well,
the numbers are,
you went from billions to millions. Okay, yeah.
right. The reason this looks so crazy is because if you compare the huge numbers on the x-axis to the relatively small numbers on the y-axis, like if I had done if I were better at making a graph, I wouldn't have put billions on the y and then just dollars on the x, right? Yeah. Because that's hard to compare. So that's where you get that. Like when you look at your change in y over change in x, I just converted that crazy decimal.
Yeah. But you could have left it as the decimal and said it in terms of the units of the graph.
Absolutely. Absolutely. Yeah.
Okay. And then the y-intercept would be that negative 39.1376 number, right?
Right.
Because it's not attached to the x. Remember, and this is very common in statistics, you are so used to y equals mx plus b, they flip that on you. It actually does make sense. I think we talked about that in another video as well.
Yeah.
It really does make sense the way this
start with the initial value, add or take away from the initial value. Yeah. In this case, your initial value tells you that when there are 0 mental health disorders, there was a negative $39 billion spent on video games, which of course is nonsense. Not every problem will the y-intercept make sense. If it's not within the scope of the data, we talked about that extrapolating concept. If it's not within the scope of the data, then it's kind of nonsense. It doesn't really tell us a lot.
No.
So
and we would never have had and never will have 0 mental health disorders.
Right. So correlation coefficient. And guys, do you see what I'm doing right now? I'm literally using all of the sentence frames that I gave you for each one of these, just using the numbers. This is the expectation for the quiz that you'll be doing over the weekend. Okay. Or this over 5 through 7, I think.
I don't know, 2.8 or something, whatever chapter we're in.
Yeah. Or is it 2? 2 point, I don't even know, whatever. In my defense, I'm working on unit 3, getting ready.
We're going back and fixing a video. Sorry, guys.
Yeah.
All
okay.
right, anyway.
Correlation coefficient.
And that 0.806 came from taking the square root of the 0.65 using a calculator.
Right. Remember, our correlation coefficient is R, and they don't give us R directly, but they give us R squared. So I'm just going to take the square root of that R squared, or the square root of 0.65, which is really close to 0.64. So square root of
64. That's about 0.8. That's fine.
Yeah. So you say the correlation of R equals 0.806 confirms that the linear association between mass shootings and rifle sales is strong and positive. Okay, if it were negative, it would be strong and negative. If it were 0.3, it would be weak and positive. Remember all of that? You got to change your words to match the number. Okay.
I think you got the wrong stem there. It should be revenue and mental health disorders.
Wow. Yeah. I think we did this last time too. Dang. The mass shootings and the rifle sales maybe has something to do with your quiz that you're going to take.
Yeah, sorry.
All right, and then your correlation your coefficient of determination, R squared, comes straight from that 0.65. And you would say, and I can't subtract. You're making fun of all these kids because of subtracting being hard. I did not subtract correctly here, just so you guys know. I'm noticing now. So about 65% of the variability in revenue in video games is accounted for by the least squares regression line with X equals mental health disorders. The remaining 45% is due to other factors like,
except it should have been 35%.
yeah, because I can't subtract. So then you would just list some factors about why you think there's correlation, or why you think that there's, this could be happening. Okay, so that's all you, however you feel.
Okay.
This, what you're seeing right now, this is a computer generated output. This is the most common way you're going to be given information in terms of this bivariate data linear modeling. Okay.
Statisticians use specific software for this kind of activity. So you would learn that if you actually did pursue a statistics major.
Right.
But
so
we don't ask you to do that.
Yeah. A random sample of 15 high school students was selected from the U.S. Census at school database. The foot length in centimeters and height in centimeters of each student in the sample were recorded. Here are a scatter plot with the least squares regression line added, a residual plot, and some computer output. Okay. Can we just talk about what we need to look at in order to have a successful problem really quick? Can we get rid of some stuff that we won't need if all we want to know is an appropriate model and a correlation?
Sure.
So over there where it says P, we don't need that. Let's get rid of that.
I got it.
Right there where it says T, we don't need that. Let's get rid of that. Where it says R squared adjusted, we don't need that. Let's get rid of that.
Yep.
It's not going to ask us anything about standard deviation, that S on the left-hand side, the 7.95. We don't need that because that's standard deviation. So let's get rid of that. And SE coefficient, standard error coefficient, let's get rid of that. Okay.
This is this is almost identical to the way they would appear on the AP exam. So you're looking for these coefficients and this R squared value. That's all you're ever really going to be reading.
Yeah. And then look at what it says to the left. It says constant, and then by constant you have 103.4, and then foot length 2.7469. Constant is going to be the one without the variable.
Gosh, my handwriting is terrible.
You call it a white intercept. You haven't been out of practice.
Yeah.
And then foot length, that's what you're multiplying times X.
And so this is the X.
So it says, is a line an appropriate model? Okay, so our line would be 103.4 plus 2.74X. That would be our line. Is it appropriate? So do we think this is appropriate?
Well, if you look at the residual plot, they sure appear scattered. There seems to be no pattern there. So I think based on this graph right here, I'm feeling it.
I'm feeling it too. I'm feeling it looks random, nice and random.
Yeah.
And then it says find the correlation.
So we got that R squared. Need me a calculator. And since that's around 0.4, I'm guessing around 0.7 because of the square root thing.
Yeah, it looks really close to 49. So it's going to be really close to 7. Yeah. So R is going to be the square root of that R squared value. The only thing I will caution you is, remember, R can be positive or negative. But when you take the square root of the R squared value, you're going to have to decide, is my R value positive or negative? Mr. Bobby's circling the slope over there because if the slope is positive, R is positive. If the slope is negative, R is negative. Remember, the R squared value tells you if it is positively associated or negatively associated.
That looks glorious.
Okay, so now it wants us to actually write that equation and define any variables. Remember, I'm a kind of a lazy person. To keep from having to define variables, I just use words, right? So
do not forget the hat on what is on the vertical axis. So we would say a statistician would say the predicted height is equal to 103.41 plus blah, 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 blah. Okay. But you're safe then because you don't have to define. Now, if you use X and Y, because you just can't help yourself, then you got to define X and Y.
Yeah, that's right. So if you put Y equals 103.41 plus 2.7469 X underneath that, you now need to, and you need to put Y hat.
Y hat, yeah, correct.
Tell me X equals foot length in centimeters, Y equals height in centimeters. It's just more writing. Just use the words, guys. By about how much do the actual heights typically vary from the values predicted by the least squares regression line? What is that asking for, Mr. Bobby?
That R squared sentence.
That's that R squared value. So what is it?
Yep, it's 48.6%. And it's actually given to me as a percentage in this case.
Oh dear. I think I did this last time too.
Yeah.
Let's reread it. By how much do the actual heights typically vary from the values predicted by the least square? No, this is given standard deviation, and it should not be.
Okay,
No, it should not.
Was right.
Predicted by the least squares regression line.
Yeah, I was right. So this is.
Yep.
Yeah, I was actually right. We had boy. No wonder that I think the video. Oop, you moved on without. So that would be what I said, the 49%. And do I need to do the whole sentence there, or or do you want me to?
Well, for the sake of this video, let's just say here's how you know the difference, okay? And this is just my fault for putting the wrong answer here. And yeah, we should have, I'm gonna go back and fix this right when this video is over so I never do this again. So I'm just gonna annotate really quick, because the thing that you're looking at here that's gonna kind of tell you what you should be using is, if it tells you predicted by least squares regression, it's asking for R squared. Now, if it just said by how much do the actual heights typically vary? That's right. This wasn't in here with X, nope. Right? Then that's your standard deviation.
Yeah.
So be careful of the wording there. Obviously, I wasn't careful of my own wording there because I should have given R squared. I actually think I stole this question from somewhere. I don't remember where though. It's been too long. All right, let's clear that screen. We're almost done, guys. Okay, so you want to explain this one?
Okay, this is a very famous set of data called Anscombe's data. They all, we actually have, you can give you the actual data, there are actual numbers that go with this. But the data, if you were to do a linear regression on all 4 sets of data, you would in each case get 3 plus 0.5x, or y hat is equal to 3 plus 0.5x. They all yield the exact same regression. And they all exactly have the same correlation, 0.816. I don't know how this man came up with this, but he must have been a genius. But at any rate, believe it or not, if we were to do the regression on all 4 sets of those data, we would get the same linear regression. Now, which of those would you say is an appropriate one to use a linear? Well, I mean, clearly this one right here is not linear. Okay. I mean, like, this is my old friend. I'm an old algebra teacher. That's my old friend, the quadratic equation right there. Right. And this one, that's like a vertical line with one freaky number. Okay. This guy, now he's a nice line, but there's a really beautiful line through that data, but then we got one weirdo out here. This is what I typically think of as a nice linear. When we're doing linear regressions, we're never gonna get them to line up in the real world. If you ever saw linear regression in an algebra class before us, you have a bad understanding of the real world. Data doesn't line up like does when you do the forearm versus height activity in an algebra classroom. Okay. It's more like this blob. Remember me circling a blob. But I have the only one, and for us in stats, this is probably the only one that's actually what we see in statistics, most likely.
Yeah.
Right.
Yeah.
All the other three are manipulated data. So just know that the R value alone isn't, that's what we're talking about here. The R value alone is not the best indicator. You really need to look at that residual. You also need to just look at the graph. I mean, pretty clearly a linear is not an appropriate model for the one in the upper right.
Yeah, agreed. Look at the graph. It's important. Graph it. Look at it. Look at the least squares regression line. Look at the residuals graph. Look at everything you can before you make a decision about using that linear regression model. Okay. Okay. So you've got to finish up your con if you haven't done that. You've got a quiz. And then Monday you have a review. And then Tuesday you have your tests. And then hopefully that next Thursday we'll get together and we will maybe have a lab. So. And
you were wanting to travel the world during this unit.
I was really bad wanting to just like visit cool places and do cool things. I'm still feeling antsy because we're still trapped months later. So
this was supposed to be back in January. It wasn't January. We were recording this back in July, I think, originally. But now
it's guys. Bye.
Bye.